It's Rogan. Good evening, everybody. Hi, my name's Obi-Wan Pez. This is Ensign Flex Pachinko. Um, Technically, we're still in an ad break or something, but I figured might as well pop over since you all came in. Thank you so much, Rogan, for coming on in and bringing everybody over. I hope you all having a lovely evening. What were you all working on? Puddle Glum, how's it going? Yep, gotta love the archives. All right, so tonight we are starting on our technically first night of talking about Calculus 3, or some of you might know it as vector calculus. We talked a little bit about this last 2 weeks ago. I have since been to Croatia. It is a very lovely place. Bit warm if you like, sun and sand, the beaches and stuff like that. Very nice. There's some other places up in the mountains more that are a bit more outdoorsy oriented. We did some river rafting. We did some uh, with both of our kids, and the information block on the river rafting said suitable for children ages 4 and up. So we thought we were probably safe. I will definitely talk about more of the experience as we get on through evening, but learning about the first dietitians in the U.S. Army. Nice. My spouse's aunt was, I believe, one of the kitchen managers in the Pacific Theater in World War II. So there is a good chance she ran in some circles with some of the people might have been talking about. I guess I also don't know what time period that was. 1970. Okay, good. So yeah, she might have run in some of the same circles as like their children or possibly grandchildren. This was also the same lady who told General MacArthur he'd stick it up. Anyway, um, I am actually serious. He allegedly allegedly propositioned her, and she was like, precisely where you can stick it. He was like, excuse me. She's like, you heard me. um she had she was a kitchen manager. She was then busted down to KP for like the rest of the war. We loved her. All right, so have as we were talking about a little bit last time, when we're dealing with vector calculus, we're going to be dealing with, well, first of all, vectors. If anybody doesn't know what those are basically any sort of, uh, it's just basically a mathematical construct which is used to denote a direction and some sort of magnitude. So oftentimes we use them as forces because forces are interesting. That was supposed to control the volume on this. Apparently is not working. I'll have to look at that later. Certainly not now. But usually we use forces as an example. So if you were thinking of, how much effort would it take to hold this book up, right? I have a force that is going from the center of mass of this book straight down toward the center of the earth, and that is at least a reasonable approximation for the amount of what we call weight. So the amount of force that it's going to, that the earth and the book are exerting on each other. Really, that the earth is exerting in the book. We're not really that concerned with the book exerting that much force on the earth, although technically it is the same amount. Yep. Have a safe drive, Rogan. Thanks so much for bringing everybody over. And yeah, just anybody who has not followed Rogan, definitely check out the channel. So Rogan is also a member of the Virginia Tech archives. So if you go to the VTUL studios, we'll just pop that on here. Okay. So Rogan is often pulling some really cool object from the library archives and going through and seeing what is there and giving some background and history on it. So definitely go check out the channels, and I don't think you're going to be disappointed if you were at all interested in learning something. Okay, so vectors, again, most of the time we're talking about forces. It could be just about anything, though. Suki, how's it going? Ian Stuckey is also one of our other friends who's in the Chicago area and does mathy type stuff. Pretty good. All right, awesome. So usually we want to signify that there is some sort of direction in terms of vectors. The directions we usually care about are the standard x, y, z coordinates in 3 space. So we typically use x and y as the 2 flat spaces that make up, your typical tables, stuff like that. And then the z space is going up and down, typically. Up is the positive direction. X and Y you can argue as far as like which direction is X. Sorry, which direction is positive on either the X and Y axes. Me personally, I usually prefer, kind of in opposition to what I've drawn in this diagram, I prefer my positive x-axis to still be off to the right, and I still prefer my positive y-axis to be sort of into the page, because in that particular orientation, I still have quadrant 1 in the, well, if I can accurately, typically I'm going to prefer that this is our, nope, positive y direction, this is the positive x direction, positive z direction. Reason being, again, I would like this to be quadrant 1, this one up here, over here, 3 and quadrant 4, so that we're doing our unit circle, our trigonometry, all that good stuff in the standard two-space x and y to be on the same flat plane unit circle coordinate system that we've always been using. It typically makes it a little more comfortable for the students, but honestly, it doesn't matter, right? As long as, and once students get up to Calc 3, generally speaking, they can look at this and be like, oh, so this is our positive x direction now? All right, so that means that like all of our angles are going to go this way instead, question mark? Makes it a little bit weird, and actually, no, it wouldn't be. Right, because this is positive x. They would go that way, in theory. If we wanted to have the same trigonometry, all that good stuff. This would be our quadrant 1. This would be quadrant 2. This would be our quadrant 3. And this would be our quadrant 4. So it's a little awkward, but honestly, it's fine. And again, the other issue is that now with z-space, this is going to break this up into octants. So now we have the space above xy plane is going to be our for z positive octants, and the space underneath is going to be the for z negative octants. Laundering a bit, nice. Okay, so we also talked about how do we look at distance in terms of our 3 space. Typically, when we're talking about distance in 3 space, it's going to be the exact same thing as it always is from our 2 space stuff. It's the Pythagorean theorem. The only difference is now we have 3 different coordinates to work with. And I did, in fact, work out a little proof here that says, hey, if we're doing stuff with standard 2-dimensional Pythagorean theorem, we can just add another dimension, and it ends up just getting us another x squared plus y squared plus z squared inside of our square root. Or, in other words, 1 squared would be x squared plus y squared plus z squared. So this also means that no matter how many dimensions your vector has, no matter how many individual things you're measuring, be they directions, be they forces, be they all sorts of other stuff, you can literally put in any units that you want and make it as many dimensions as you want. You just won't be able to visualize it very well. Then again, we'd be able to just say, okay, however many dimensions you've got, if you just want the standard distance in our typical metric space, in our typical measurement, then all we're doing is we're just saying sum up all the squares of your dimensions. That's it. This is only measuring from 0, so you have to know where your origin 0, 0, 0 is, and then you're going out to some point x, y, z. So it is x squared plus y squared plus z squared is equal to our v squared. The distance of v squared, magnitude. The magnitude, there's the word, of v squared. I am going to get a little bit punchy tonight because I haven't been on in almost 2 weeks, so... okay, and then if we want to look at the distance between the endpoints of any 2 vectors in our 3 space, then we came up with our 2 coordinates, x1, y1, z1, and x2, y2, z2. And we said in order to get the distance between them, we're just going to look at basically doing the same kind of shadow thing, where we're just drawing the right angles that make up these particular distances. And we can draw a right triangle that goes from one of the vectors to the other, from the ends tips of the vectors to the other. And that gets us our otherwise we start getting moths in here. It's very fun. It's also possible they're not out tonight because it's a little bit wet. Right. So in order to figure out the distance between the two vectors, what it amounts to is finding the distance or the difference between their x-coordinates, between their y-coordinates, and between their z-coordinates. And then those become the new distances. Another way to say this is that our x1, y1, z1, because we're subtracting it, becomes the new origin point. We're effectively shifting our origin point from 0, 0, 0 up to x1, y1, z1. And then we're just figuring out our standard distance the same way here, but now with x2, y2, z2. So, super awesome. And if anybody has any questions about other math type stuff, feel free and stop me. This is mostly just me going through, I forgot to introduce the book, cracking the GRE math subject test. This is the graduate record exam, which is required for most students of, well, anybody who's intending to go into a master's program of mathematics or something very similar. I ended up taking this exam in 2004, so that gives you an idea of how old the book is. Because this is the very book that my spouse and I used to study for the very, let's be honest, study. I poked around a little bit at the things I literally did not know. In addition, we want to talk about the dot product, which is a particular kind of multiplication that exists within vectors. Sorry, I got a hair bothering me. Oy. What happens when you don't trim your mustache? So if we have two vectors, A and B, and we want to do dot product, this is going to what this is going to do, right? There is a hope this doesn't yell at me much. Apparently, I did not start my computer, so hopefully I can ditch. Can ditch a few processes. Should be okay. Maybe. Oh no. Okay, so the idea here is that our two vectors A dot B, when dotted, this will get us the A and B are going to be the respective magnitudes of those particular vectors that you had. And also theta is the angle between them. Ah. Bar. Okay. Okay. So A and B are the respective magnitudes. We could also denote this as magnitude of A times the magnitude of B times. Okay. If at any point this stream just dies, I will probably be back in about 40 seconds. That's the minimum amount of time that I have getting back on. Anyway, it should be fine. It'll be fine. Let's take this, do the notes over here in a different color just so that we can actually see it fairly well. This is also called the vector projection. Of B onto A. So if we were to look at the way in which you could project, again, vector B onto vector A, you took a light source essentially and kind of like moved it around to project the shadow of B onto vector A, then that's what we're doing with the dot product. So we can see an example of that. If we were to go with also shorthand. Projection sub A is projection onto A of, just like our regular function notation, right? Put parentheses around B. All right, and there's some nice nice diagrams in here, which I attempt to copy. Getting dangerous. I'd at least better look. Okay. Guess it's got a lot going on. Fire. Okay. zombie process. That'll be fine. Not just the processing power in. So anyway. So if we were to draw out a diagram, let's do lines, no sloppiness, cool. This is our theta, so it's, again, the angle between them. What this is going to do is look at the horizontal distance that B is going across A, but like relative to what? Well, relative to A. So if we were to take A as it is and then draw down a right angle, then this distance right here is going to be, again, proj sub A of and in fact, if we wanted to go the other way, right, if we were to draw, not quite a right angle, but it's close. If we were to draw, that's better. This just right here would be proj sub B of A. All right, we're going to talk about a little bit of that in like a couple minutes here, but if you look at it in terms of like what's going on, again, we're looking at the cosine of theta. So if you remember your trig, hopefully if you're doing Calc 3, you remember your trig. Cosine is the adjacent divided by the hypotenuse, the length of the hypotenuse, which in these cases, right, our cosine of theta is going to be equal to the projection of B onto A divided by magnitude of B, which is going to be the hypotenuse of the green triangle. Right. And okay. Right. That goes. All right, there's a nice little proof in here. I just want wasn't going to go way off. Right, so the magnitude of b times cosine of theta is going to be equal to the projection of b on a. Okay, so this also has a nice little addendum onto it to make sure that we understand okay. This is also in the a direction, often used as at. So because we're using the a vector as the direction vector, that's also going to be direction. Sorry, not times. Just so the direction note that we put on this. So the hat is just telling you what direction it's in, which is also a vector divided by its magnitude. Okay, then this ends up coming over, and we end up with magnitude of a vector, magnitude of b vector, cosine of theta is equal to this whole mess. Direction, and then we have the a vector stuck at the end of it. Anyway. This is how we can pull this particular formula from all the little bits that we had up here. Should be noted that when we want to do this like algebraically and just get some values with it, if we have a vector dotted with b vector, normally I make vector dot products a little bit thicker, a little bit bigger, whereas the scalar products I just put as like a tiny dot. In theory, they're the same thing because when you try to do dot products with scalars, they just multiply. So it ends up behaving exactly the same as vectors, but they just don't have a direction to them. They only have their magnitude. Okay, so if we let A2, right, we just do A1, A2, A3, or it can also be rewritten as A1I plus A2J, A yet, plus A3K, A hat, I hat, J hat, K hat. And B vector can be B1, B2, B3. Or I hat plus J hat, K hat. Then what we have is we're going to do the dot product between each of these things. A1 I hat plus J hat, K hat, dotted with U1 I. Right. So with these being effectively in this algebraic notation, we could in fact just multiply all of them together as if they were just our standard like trinomial times trinomial. This has a special outcome, which I'll let you know about in a little bit, but just to see it, right? So here we have A1I hat, B1I hat, plus J hat, K hat, A2, A2 is A2, K hat. A3, K hat, B1I, K hat, 2, B, okay. The issue here then becomes the scalar pieces are easy enough. We just shift them around and multiply them together just as you would any other number. But now what about all these I hats and J hats and K hats? The issue then becomes, well, now we're multiplying two things. which are at right angles to each other. And if you remember, the way that we were looking at this was, right, what is the projection of, take a right angle, take the tip of one of your vectors, and you're saying, okay, it's this vector projected onto the other one at a right angle. We draw a line going down, and then look at the distance that would be covered by effectively a shadow, midday shadow that's coming straight down at a right angle, forms an altitude on A. What's the distance that we get for the shadow of B on A? Well, got a bit of a problem there. Right, if we're trying to find the projection of J hat onto I hat, there isn't one. Right? It doesn't exist. So anytime that we end up with a multiplication of, or dot of, our I hat with either J or K hat, or we have J dotted with I or K, or we have K dotted with I or J, then all of those are 0. Because the projection of this thing is only that single point. No distance. So we have a 0 distance. I hat dot J hat 0 and true any perpendicular. Okay, so I with J, I with K, J with K, K with J, K with I, J with I are all 0. Which means that we only have 3 vectors, 3 vector multiplications, which are not 0. It's going to be A1, B1, I hat dotted with I hat, A2, B2, and J hat dot J hat, plus A3, B3, K hat dotted with K hat. So now what, right? What is the distance that we get when we dot I hat with itself? Well, it is I hat. But even more specifically, like, what is I hat? Well, it's a unit distance, so it's just 1. So anytime that we get any vector dotted with itself, it's just going to get us 1. So we end up with right, A vector dotted with B vector is going to get us A1 B1 plus A2 B2 plus A3 B3. And this is going to go on again if you have a higher dimension vector, then you're going to end up with more dimensions in this. So it's just always going to be, I guess we could also say that this is going to be the sum as I goes from 1 to n in an n-dimensional space. We're going to have a sub I, b sub I as the product, all summed together for all different i's, a1, b1, a2, b2, a3, b3, a4, b4, all the way up through whatever n is. In this particular case, n is 3, because we only have 3 dimensions that we're working with, I hat, j hat, k hat. Okay. All right. Again, anybody have any questions on either this or any other math you want to talk about? Feel free and stop me at any point. This is just going to be a reference guide for what I would like to do for the evening. I always will prioritize any questions that come in from viewers. Wednesday nights are our big math calculation type nights, and I do it basically as long as I can put up with myself. And then, generally speaking, we'll go out and raid some other educational channel. Isn't this the evening for you? Yes, I usually start at like 9. Actually, that's not true. I usually start between 9:30 and 10. So, yay. 10:52 at the moment, and I am almost done with my coffee. Ooh. Oh no, I just meant this evening. This is the um, this is our like, if I'm honest, right? This is basically something to do between students asking questions. We give it structure. But the fact is that most of the time people don't ask questions, and so it's like, what else am I going to do? All right, we'll just go and have some fun here, and put a little bit of structure into it by saying we're just going to work on cracking the GRE, and then someday we'll go pick up a different book. I will say, this weekend when we were in Croatia, I ended up picking this back up and made some more sense out of like a good 2 or 3 pages, which I took PDEs in grad school, but that was basically 20 years ago now. So been a while since I've done anything with PDEs, and I kind of still want to have that expertise in like, generally speaking, differential equations. Yeah. um Right. So some other ones that we could have done, if we had drawn two things at right angles, again, now we're saying that, well, if we have two vectors here, then again, this is just going to say, okay, there is no projection of onto A. Is no projection of B onto A beyond a single point, so our distance is 0. Whereas up here, we ended up with A dot B got us that formula again. And also in this particular direction, we end up getting a positive number because our distance is in the same direction as A itself. Now, this is also very important because that foreshadows what happens when your cosine ends up with an angle that's larger than 90 degrees. Again, if you remember your trig, which if you're taking Calc 3, I certainly hope you do. Right, and then we say that, okay, here's our A vector, here's our B vector. Again, we want to go perpendicular to the A vector. So perpendicular to the A vector ends up, man, let's switch this to dotted because I can't trust myself. Good enough. Right, so perpendicular, not too bad, roughly there, ends up over here. And so the distance that we get for this with an obtuse theta is going to get here the projection of B onto A, which again is going to be just dot B no, wait, that's right. Projection bit is the distance. I'm sorry. Is the distance. There we go. That's why I was confused up there a bit. I was trying to yeah, I was speaking straight from the rectum. It's not that this is equal to the projection, it's equal to, again here, our projection dotted with A is going to get us all of that stuff. So it's A dot B and it ends up getting us the same as the projection dotted with A. So when we look at this down here, again, this is our distance that is going to come out of this. The projection of B onto A is that distance. And you'll note that this is in the opposite direction as A itself. And so because of that, our cosine of theta, is beyond 90 degrees. Cosine in the second quadrant is going to be negative. So greater than -1, of course, but you know. Put some limits on it. Make sure we know where it is. Okay, so when we vary what direction A is compared with B, then we end up varying value of our cosine of theta. We end up changing the dot product of things. And so this is going to get us, in this particular case, a vector dotted with b is going to be less than 0 in this case as well. Here, a dotted with b is 0. Up top, we greater than 0. These, for this particular setup, again, a theta. Should also be noted that, right, we're sharing, we're sharing distances here, or no, not. We're sharing the angle theta here. Our two triangles also have right angles, and so because of that, they are wow, sorry, they are similar to one another. So this is going to tell us that, right, the really S for share. Point names. These are terrible. Why would I want point names? I hate it. Sure, M and N. Saying that triangle SON similar to triangle SEM by angle-angle similarity. So what does that mean? Well, it means that all of the corresponding side lengths are going to be in ratio with one another. So our projection of A, shouldn't do it. Fine, but you know, projection of B A divided by A onto B is going to be the same as ratio between the magnitude of B, magnitude of A, equal to distance ON divided by the distance PM. So all of these things we can relate to one another, showing the similarity of the side lengths, and then we could like come up with other relationships if we felt like it. Yeah, I thought for about a half a second that I would be able to show that A dot B should be the same as B dot A. That's actually much easier to show algebraically here because our whether we have A dot B or B dot A, we're going to get the same diagonal terms, which are going to not be 0, and everything else will be 0. None of the other stuff matters. Oh. Ab break's about to start. I'm going to bring that downstairs anyway. I hope you all are having a good night. Get up and stretch and walk around, do whatever you need to do, and we'll be back in, roughly speaking, 3 minutes. So thank you all, everybody, for coming. My name is Obi-Wan Pez. This is Ensign. Yep. See you shortly. Okay. So we're going to nothing. Sometimes I get paranoid. All right. Instructor things have been basically, if anybody wants to follow along, what we do. Final create that little bit of got little folds essentially join part that creases when you bend sort of like turn to one side, pivot on the hip, and to bring leg slash abdomen together on the side. It also offers a lot of springy tension up. So the muscles in that area tend to create what is called the chi, energy that you can draw from in order to boost power. So oftentimes, a little bit of warm up, we kind of let yourself relax, burn, trunk rotation, but instead of letting your arms fling out in front of you, you're going to do let front one come up front, let the back one come up back behind, and kind of twist a bit and guide them. Don't lift. If arms were like swings on a swing set. And then as you get back, kind of tuck in, final creep, duck a little bit on each individual side, and then push out of that side, and it causes front arm, back arm to less pronounced. Kind of whip down in front of you. And when we're done with that, do another one. We can let the arms kind of fall in front, and then we duck or pop the knees a little bit, and you automatically your arms and let them fly on their own. We also do one front and back. Go from rock your weight from the balls of your feet, from the balls of one foot to the balls of the other foot. Let your weight come forward and backward, and then it causes your hands to, again, swing up in front of you, and then switch front. Whichever one's in front, just you may need to turn. Right, then okay, so I don't know exactly what the So now we check this. I think this is going to be better. So let's see how it goes. So we're going to, again, just let your arms swing both in front when you're doing these and then back and forward doing these. Kind of want to make sure let your hands fly, just as, again, as if they were kids on swings. Just rock your weight back and forth, and that should do it. Okay, so the actual form itself is a bit long, but nonetheless, it's good stuff. So we stand originally as bear, which is we let the hands kind of fly out just a little bit away from ourselves here. And then we're standing with our feet in a V shape in front of us. And we tuck into the right inguinal crease here while stepping left and then straightening out posture. Breathe in for 2. Out for 2. From here, tuck into the left inguinal crease. Come over as if holding a ball of energy. We turn on the heel of the right foot and then allow ourselves to over to this side and then step forward with the left foot. Switch to a left ward-off position, which is essentially just coming out in front of us like this. And it's making sure that if somebody were to attack us from the front, like the hand is going to be the first thing that they're coming in contact with. A lot of stuff with Tai Chi, basically you just want to keep contact with the other person and go from there. Right hand sort of stays floating back here just in front of the body, and then we turn the right back foot and lean forward into the left side. Then we, since we're leaning forward, we're going to turn on the toes of the right foot, which is back behind us at the moment. And then we go to a right ward off with the left hand up as well. Then we rotate in, rotating the back leg in position. We do a roll back, bring our left hand down approximately to our right elbow. Come back through like this. We're going to guide somebody's attack past us. When we get to here, we bring the left hand back and around, put palms together and press. And when we shift all of our weight to the front, we break apart, come back, and then push. Once all the weight comes back to the front again, then we're going to hold the hands out, come back to the back leg, and then we swing forward in a very awkward sort of pigeon-toed stance. And then as we tuck into the right inguinal crease, pulling down like this, we do a single whip here. This hand is just staying underneath. And then as we whip this out to the right, the left foot then twists around as well. So now we're going to be here. Step out left and bring the hand out. And then as we move, shift our weight forward, twist the back foot, and twist the hand back to a front position like this. In the form, right, toward the beginning. So since we do a single whip here, okay. Right, since we do a single whip here, we're going to lean back, going to twist the Foot, no, we don't do that yet. Sorry. We come from here, bring the feet together, and we step on the right heel, just barely touches the ground. And then here we do lift hands. Bring everything back, including the right foot, and then we step forward, do a shoulder strike, and then from here we're tucking into the right inguinal crease, turning the right foot over, and then we do white crane. So left foot comes up. I'm really far too close to the camera for that. I'm going to do this in my kitchen someday, so we can actually have it documented. Right, then from here, come down to brush knee, step up with the right foot, swap positions with the hands, pick the left foot just in front of us, standing on, and just barely touching the left heel to the ground. This is strumming the lute, at which point we do another brush knee here. Then, once we get to that position, we lean back to the right leg, come forward, make our fist with the right hand, and come diagonal with the foot. Twist around, step, basically like stepping kind of foot pointing forward this side of the room. You do a backhand or parry here. This is another parry. And as we step through, strike here in the back leg. From here, we do a Rufung Subi, where we kind of, oh, it is up top. That. Rufung Subi allows our hands to come under like this. We tuck into the left inguinal crease. We take over the pressure from our right hand onto the left arm here, set back, and then push forward. Come back again like this. Do another pigeon-toed stance to the front, break, and move our feet parallel to each other. 70% of the weight still on the left leg. Come up like this and rest the left hand weight on the right wrist. Then turn on the right toes. Come out this way. And then from here we do carry tiger to mountain, which is a decent step, about 135 degrees out that way. And then what we do with the hands, bring it back, and as we're turning the left foot, we also come through with the hands and strike. And it can either be a strike, or essentially what we're doing is we're taking somebody who's really, really aggressive in front of us, and we're just basically throwing them that way. So. Then when we do that, we come back up, do a roll back, roll back, press, push, another one of these. But here, we're going to the corner of the room rather than the side wall. Then we come through this way. Again, lean back, turn 45 degrees on the front leg. Go this way as we shift everything. Not this time. Right? As we come down, we come through with a slap strike with the right hand. Comes through like this. Both arms come back. Step forward with the right foot, and then we step forward with the left foot, and a again, we're barely stepping with the left foot, just heel basically touching the ground right there, and that's it. And then this right here ends up taking most of the like forward momentum and transferring it into whatever the target is in front of us. All right, fist under elbow. Then repulse monkey. I think it's repulse monkey. Come back around. This hand comes back around to about the ears, and then we step back. We have both hands like this. And here, this hand comes back up to about where the ears are. Step back. And then this hand comes up, and we do one more. In theory, I have backed up. We are then going to turn, hands reversing their direction, step out 135 degrees again, come out this way, and then we press. This hand goes up generally into a target here. This hand comes down here, and then we curl to an energy ball here, curl into the right inguinal crease, and then we step left. Cloud hands come across. Step not quite together, but feet closer. Step left, and then step more or less together. Step left, and we step forward, and then the ward off comes in front of us here. We then curl in, duck everything down, put the energy into the right inguinal crease, and then we turn, do a single whip this way, and our single whip this way, and then a hand down here. We take another big step forward, bring this out, lean forward, and set our left hand forward like this. Then we're going to turn 45 degrees with our left foot, duck down, and grab essentially the calf or like the pant leg of somebody who's here, and we basically just throw them up, and then come to a block, put the foot down, switch other way, and then as we're coming down here, what we're going to do is we're going to brush hand coming across, and then this one also. Basically just bringing this in a nice big circle. This is going to brush ideally around the target's face, so hitting somewhere around the eyes. Do something like that as you're coming back. And generally speaking, people don't like that. And so they'll be like, whoa, okay. Especially if you have very good control and very good power. From here, this is the bit that I forgot today. So this is why I'm doing it. And I will probably have to redo this many times. But nonetheless, so we come through like that, brush across. Then we're going to do a rollback here. We turn on the right heel. And then we bring this one around and do essentially, it's like a little bit of a capture here. We turn on the right ball of the foot. Now, since we've kind of walked our foot closer, it also gives the other person the illusion that we're further away than we are. And so we kick. After we kick, we set down our foot further away, and then we got to do the same on the other side. So basically here, we're going to go around. I'm still that way. Come around. No, that's not it. That way. We're now leaning on the right foot. And we do basically the same thing, where this is going to come in and down in a boy, roll back. There we go. So we roll back, and we curl our body inward, bring this around, and as we do the capture here, we bring our left foot in closer, and then here, this is again a toe kick in this direction. Set our foot down back behind us, roughly even with the toes, even with the heel of the right foot, and then we turn. As this comes around, right, we turn on the right heel and the left toe at the same time, lock in with this, and then we do a heel kick, which my instructor says at this point you're sort of thinking of somebody coming at you, and so you want to bring this up as a guard on your left side. Do a heel kick, and then your right is also going to be prepared over here, or you've just come up to block something. At which point you do a brush knee, come back, turn 45 degrees, do a brush knee the other way, lean back, turn 45 degrees the other way, and this time you do a brush knee with the left, but the right does a really low punch. So this is going to be, roughly speaking, right under here. So you hit somebody basically at the belt line, like that. And he also said the other really great thing about that is you can get the forehead involved and like crack them. Ideally, you're not going to hit them in the face, you're going to hit them like here in the solar plexus. And if you hit somebody here with your forehead, first of all, they're not going to know what to do with you. And secondly, if they've just been hit in the solar plexus, there's a good chance they might not be able to breathe for a second. So it gives you a second to relax a bit. You bring kind of all of it down at once. And then from here, we do the lean bit again, 45 degrees, step forward into a right ward off. Roll back, press, push, here, back to single whip, comes out, that, and then from here we do a section that's called Fair Lady's Hand, and I don't know what to do. I don't actually, I have not learned this yet, but I've seen it a dozen times. But it's something to the effect of like our hand comes up as a guard, and then this one comes out as you're dipping your hand waiting for a kiss or something like that. But it is very silly. Honestly, I can't wait to learn it. It's just everybody says this is like the hardest part of the form before everything else is just super easy. So we'll see. So thank you for indulging me. Those of you who are actually still around. It is, as Ian Stuckey says, take care of the creature that you are. Obviously, I need to take slightly better care of this creature that I am, but nonetheless, Tai Chi is an excellent exercise. I don't necessarily mean the Tai Chi in the park, but the Tai Chi Chuan has been treating me very well, and is a very active sport. So if you can get into something either called Tai Chi Chuan or pushing hands, or another of the awesome martial arts that are out there, find some place that is reputable that doesn't just have you pay for belts in order to earn them. I did one through the county Parks and Rec, and it was basically like, I don't know, $300-400 a year, and I did it for 17 years. So it was wonderful. They only ever put me up for belt promotion if they thought I was already going to get it anyway. And you get what you get out of it what you put in. So I usually would come home every single week, absolutely soaked through my gi, and felt really good. The next couple of days I was pretty miserable. But when you come home from the gym, you feel really excited and the endorphins are kicking in and all that. Yep. Our tongue sudo karate basically did the same thing for me as a good workout at the gym. Okay. So let's get back into it. Here we have the dot product that we were talking about. And there is one other that we need to definitely talk about, which is the cross product. So the magnitude of cross product is going to be equal to the magnitude of A times the magnitude of B times sine of theta and it's in a direction. It's in a direction, yes. Damn it. It is in the direction in accordance with what everybody's favorite thing is, the right hand rule. So I guess we could just call it H hat for now. Cool. Ugh. Rotation. All right, this will work. H is the direction of the vector perpendicular to the plane of rotation from A to B, in accordance with the right hand rule. But realistically, right, if you're along the plane of rotation from A to B, then like it doesn't matter. I mean, it matters which way you go. Eh. Yeah. Um, Fine. That'll work. So if we're going from, a particular vector A to a particular vector B, now keep in mind I'm doing this in 3 space, right? So A is going to be kind of this way back toward the light, and B is going to be toward the camera more or less. So here, in accordance with the right hand rule, from A, this side, to B, using my right hand, we're going to curl in this direction, the direction of my fingers. So from A to B, and now the thumb on my right hand is pointing that way. So perpendicular to the rotation, our cross product is going to be in this direction over here. Now, some people might be like, where in the hell is this going to be used or useful or anything? And I was actually driving one day and I realized just how necessary like the cross product and all these vectors were interrelated to each other when I went like this on the steering wheel. And so I was gripping the steering wheel and I pointed like this and I said, okay, so the position that my hand is on the wheel is given by the finger that is pointing into the wheel, like into the actual material itself, which is going to be my pointer finger. As I'm trying to turn, this is slightly different maybe, but the velocity of the motion that we are making is along this vector, my thumb, which is tangent to the wheel, right? The velocity of motion as I'm turning the wheel is in accordance with my thumb. And using those two vectors, right, we now have the cross product of the position vector and the velocity vector of the motion around a wheel is going to end up getting us curling from, I guess, from the velocity to the from the velocity to position is going to get us a vector that's headed into the center of the wheel, which I then realized is the middle finger in this particular arrangement, which is giving us the acceleration of that motion. Right? As you're coming around a wheel, the acceleration is in toward the center of the wheel. You have your position, your velocity, and if you do velocity cross position, you end up with acceleration. I was like, I mean, maybe it's just the direction and not the correct magnitudes or whatever, but the realization hit me all at once. I was like, oh, that's going to be helpful. I did turn that on, right? Yes. Okay, good. That would have been very embarrassing. I've definitely done that before. Just been sitting here chatting with nobody because my microphone didn't work or whatever. Whew. Good news, since I got this new microphone, it's all worked predictably. Bad news, I still need to get some sort of mount for it, and I don't know where to put it. Most likely off the back of the desk, come up over the top of the monitor, come up over here or something like that. But I gotta work that out because I don't have a mount. It'll happen. Okay, then, and thank you so much for the follow, Jester Cakes. If anybody does have any questions about math generally, teaching, anything like that, I'm here for it. The stuff that I'm talking about here is Calculus 3 or Vector Calculus, and if you have questions on that, feel free. Otherwise, if you just have other math questions, tonight's the night for it. The stuff that I'm doing is just serving as like a frame for the sorts of stuff we're going to talk about if no one else has questions. So feel free and ask anything. I'm very happy to answer. Right, so this doesn't involve H. It's only when we take away the magnitude itself and say this is A cross B that we end up with that H hat at the end, which is also getting us the direction, right? So the just scalar portion itself no, exactly the opposite of what I said. The scalar portion is just that magnitude of A times magnitude of B times sine of theta. Again, these are scalars. The scalar portion of A and B. Now is a good time. If anybody is interested, this is Jason Chalmers Miller. Musician, voice actor, awesome guy all around. Did a bunch of projects with Critical Role and Geek and Sundry, including music. He composed a number of GNS theme songs, including Your Turn to Roll on Critical Role and the season 3 theme. Oh, Your Turn to Roll was season 2. Season 1, season 2, I think also some of season 3. And he also did some work with Blood of the Void and Clear Skies, the Star Trek RPGs run by Eric Campbell. Also known as 8-Bit Eric here on Twitch. While I'm shouting out awesome people. Oh. Wrong. Oh, 16-bit Eric. Jeez. I'm a whole generation behind. Hey. Oh, man. I'm alright. Promise. So, yeah, go check out 16-bit Eric. He does all sorts of stuff. Was playing Darwin's Paradox, which was cute. Inky Boy. It was an octopus type game. He had to run around the ground and swim through a bunch of really dangerous areas to escape the lab or something like that. I think it was escaping a lab. Anyway, that's cross product. So So there are some interesting consequences which come about because of this. One is that if we were to cross cross B with A instead of A with B, we do still get this whole like A times B times sine of theta, because none of that changes. Right? If we do one from the other, that's all going to be exactly the same. The magnitude of A, the magnitude of B are going to be the same regardless of which order we cross. The sine of theta is going to be the same regardless of which order we cross them in. However, the important part is that now, instead of A cross B going this way, we now get B cross A, which comes this way, and now it's going that direction. So this is very interesting because our A cross B was this way, our B cross A was this way. They are exactly opposite each other. So this is going to be times a negative H hat which is negative parentheses A cross B. Every single time. Always works that way. Right, the angle between these two vectors is always going to be the same value, theta. It's just now we're going in one direction versus the other. And like we did in trig, right? If you're going one direction versus the other, they're opposite of each other because we're going in opposite directions. Okay. And this also has an interesting other consequence, which is that if we were to draw regular, if we were to draw A and B like this, and again, we draw in this right angle, right, the altitude from B projected onto A, just like we did for the dot product. So this is A dot B would be the distance that we're looking at here. It's important to note what other measurements we have. So like that's not A dot B because A dot B includes the other vector. Sorry. this is the projection of B onto A. All right, this is also B cosine theta. And it's also important to note, like, what's this one? Well, this is the sine of theta is going to be our x over the magnitude of B. So sine of theta equals x over magnitude of B. So our x is equal to magnitude of B sine A, or sine theta. So with that, now very interestingly, if we were to take this altitude and then multiply it by the hang on, that on here. Yeah, you know what? Let's just take all this. Take all this, right? And then we were to multiply it by all of this, which is the magnitude of A. Well, first of all, this is what we have for our cross product, right? So our magnitude of A times magnitude of B times the sine of theta. We take these things together and multiply them. This is going to get us a rectangle with the base of magnitude of A and the height of magnitude of B sine theta. However, this is not going to make a rectangle, at least not very nicely. However, is going to make something else very nice. This is going to get us the area of the parallelogram defined by vectors A and B. If we were just to then say, okay, where is the location of A plus B going to be? Right, so this vector right here let me rephrase that. The diagonal will be, right? Or whose diagonal is a vector plus b vector. So here we have the area of all of this is going to be called, again, the cross product, or the vector product. And because we have this very cool property here, this is also what's known as anti-commutative. Right, commutative property is where you have a multiplication or an addition where, for example, it could be anything, but in this particular case, we have this operation which doesn't matter which way it goes. The scalar multiplication, for example, right, a times b is the same as the scalar multiplication b times a. So that is commutative. Scalar multiplication is commutative. Scalar addition is commutative. Vector addition is commutative because we could go a plus b, or we could go b plus a. We always end up at the same place regardless of which one we end up doing. So those are very cool properties. This one is even cooler. It's anti-commutative. So the cross product of these two vectors is going to end up getting us opposite values. All right, hang on. I guess technically, right, it's not this exactly. It's that times the vector that we needed. So right, that's our cross product. That's what's actually equal to a vector times b vector. Okay. Oh, that's weird. This page is missing the actual cross product symbol between each of the sets of vectors, so it's just messing with me. It's fine. Fine. So I cross j is going to end up being k, which is then the opposite of j cross I. J cross j hat cross k hat is going to be equal to I hat, which is the opposite of k hat cross j hat. And then I hat cross k hat is going to be j hat, which is the opposite of k hat cross I hat. All right, ads are going to roll. We'll be back in 3 minutes. This time we'll do just a very short amount of weightlifting, and then we'll get back into it. So See you in 3 minutes. We'll be right back. Go stretch, cycle that water, do whatever you need to, and we'll be back in 3. Thanks so much, everybody, for coming. We'll talk real quick about how to look at the cross product in another way using matrix multiplication. So, see you in just a little bit. Yeah, sorry, I left that hot micing, but hey, nothing really happened anyway, and no sound was made on this side. So it's all good. All right, just so in hoist. So start with 20-pound weights, and let's do standard arm curls until we reach pretty close to failure. At which point we switch to shoulder lifts. I don't know what to call it exactly. It would just come up under the shoulder, up under the armpits, and then we switch again once we're again pretty close to failure or just bored, and then lift one 20-pound weight up over the head. right, that's about it. Deltoid lifts? What do you call these? All right. Now we go up and over. You have to be careful anytime that you are lifting weights in general, but especially if you're doing it up over your head. This could be super dangerous if you are not watching where this is in relation to your skull. In addition, you notice that the shadow was looking very large when I was doing it over here. I want to stay away from any sort of hanging objects. And never drop a weight unless you know exactly where it's going and unless you are pretty confident that the ground will not break. 20 pounds lifted to a height of roughly 7 feet is not somewhere that you would like to drop it from. That'll cause some problems. Good times. Righto. Oh man. Just reaching up is like muscles are all half numb. Good times. Okay. What we see over there is going to, there we go. What we see over here in blue is the list of any particular vector being multiplied by any other particular vector. I should probably change the I and K one, which is going to get its next vector in the cycle. So that's why I should probably change it. Good news, we just can shift these around. We don't need to break everything. That'd be silly. That'd be a whole lot of work. Why would you want to do that? So yeah, I times j is going to get us k. J times k is going to get us I. And k times I is going to get us j. So we can think of this, the book here thinks of it as a cycle. And so here we have the cycle of I to j to k. And again, if you do it in that order, that's how we get it. If we go in the opposite, order like these, right? K could also get us j cross I, but negative, right? In the opposite direction according to this particular setup. It's also important to note that I cross I, j cross j, or k cross k are going to get us 0. Because in this case, right, we're taking I hat, and when we cross it with I hat, right, This is also I hat. What's the area of the parallelogram created by these two vectors? Well, they're indistinct from each other. So there is no area that can be defined by two vectors which are laying on top of each other. So we end up with the cross product of 0 for any of these vectors. Any vector crossed with itself is always just going to give you 0. Right? Another way to think of it, right? You're looking at the rotation between A to B, right? A cross B. Look at the rotation between A and B. There is no rotation. So if there is no rotation, there's no way to tell what direction is perpendicular. It's literally every direction at the same time. So H is ill-defined, and so therefore we could say, okay, well, the cross product of these two identical vectors just doesn't make any sense for us. All right, and with the other stuff that we're doing, we might be able to also see that right, A cross B plus C is going to get us, in this particular case, we could say like, okay, well, let's come up with 3 vectors in just 2 space. Fizzbuzz, how's it going? I know, I finally joined the club here and started doing vector calculus. So here, yeah, I mean, we reached the appropriate section, is which is on page like 100. So we're there. Still got that left. Allegedly, need to cover basically all of undergrad math, so. Oops, no! I hit Control N instead of Control V. Oops. Ooh, so close. Almost. Okay. So if we woo, okay. I hit the button on the stylus. If we want to, that was weird and slightly gross. Don't do that again. All right, this is B plus C. So, if we now want to cross A and B plus C, we would then take the parallelogram created by A and B plus C and try to find its area. No. So I am using cracking the GRE as kind of a frame upon which to draw problems and have like some sort of structure to my Wednesday nights. Before it was like, I'll just pick up like a book and start doing a couple of problems out of it, but then like, I generally speaking, it was like I'd get bored or I'd run into something that I couldn't really do. So I was like, you know what? Let's just do all of all of undergrad mathematics basically. I know I could probably do it. Right. So this is now going to be, again, the area of this is going to be um, the sine going to be the magnitude of b plus c times the sine of theta. Theta is going to be from a to b plus c. Hang on, do I have that? Nah. I don't have my Steebs emotes is the problem. Oh, that's all right. It was like 99% of the time I go and hang out in Aaron Stevie's chat, and if anybody here does not know Nair, um, Nair is notorious for buying gift subs for like basically entire communities at a time. Almost invariably, I would just like park in Steve's chat for a bit and get a sub from usually Nair. And so I would have emotes from Steve's channel, one of which is a sign of no you. No, you're awesome. All right, so this would be the magnitude of A times the magnitude of B plus C sine theta. And then this is going to be in the direction coming out from right. Hey, chat. That's totally what that looks like. Yeah, coming out from the screen as opposed to the stuff that's going in here. And technically this would be negative h hat, but we hardly mention that. Oh, Moohoodles is the other one. Nair loves to hang out in Moohoodles and Steve's chats and give subs like they're free water bottles at Burning Man. Okay, times h hat. Now, the product of A and B plus C, again, magnitudes, is, yeah, this, I'm pretty sure that this is going to be, oh shush. Just haven't reset for the night, whatever. Sine theta times h hat. I'm pretty sure that this works this way, right? Because, oh, no, never mind, no, it doesn't do that. Triangle inequality. Hope nobody saw that. Okay, then what if we had A cross B plus A cross C? Right, so then this is going to be A cross B is going to be A times B, magnitude, times the sine of theta in the h direction. It's still the same direction because going from A to B and from A to C and from A to B plus C is not going to make any difference at all. It's all on the same plane. Okay, plus. Here we have the magnitude of A times the magnitude of C times sine theta h. No, not vector, h hat. All right, which is magnitude of A times magnitude of B, like parentheses, magnitude of B plus magnitude of C. So, that is a tiny bit of a problem. So, what is A cross B? A cross C, what do their individual parallelograms look like? This is A. You know what? Hang on. Shift. Like that one. And also that one. Yeah. Copy. Bring down. Paste. I don't want anything else other than those three vectors. And our A, our B, and our C. Then I want to take individually C. You know what? Let's make C salmon colored. And we copy and paste. Give it to A to make that parallelogram. B, just turn white for now, copy paste with A as well. All right. I don't think that there's a nice way that we could like do geometry, add these things up, and be like, look, they're the same. I just don't think that that's going to happen. Or let me rephrase that. I don't think there's any way that I could do that. Let's just clear some of this other nonsense out of here. They're from last week, so it's not like it really matters anyway. I wasn't even looking at these tonight, so like... Oh, right, let's just click that and go back to 100. Plenty of space now. Okay. So what we really care about here in this case, though, is our B plus C. If there's any way to do some geometry on that in order to show that the b plus c, well, a cross b plus c is going to get us the same thing as these two separately. That I don't think I can do, just offhand. And again, maybe it's just me and not like overall, but nonetheless. Okay, so this one, we can drop an altitude. This is going to be the angle between A and B, we'll call beta. And angle between A and C, we'll call gamma. Right, so this is 180 minus gamma. Then means that this one here is going to be 180 minus that. Can't be gamma. No, right. It's 90 minus 180 minus gamma. Parentheses. And this is going to be negative 90 plus gamma. Right, gamma minus 90. Get that amount. So same on this side. This is going to be gamma minus 90. And this one is 180 minus gamma. AB sine theta. No, that's AB sine beta. Um, this is going to be a C sine 180 minus gamma. When we subtract that, or when we do the subtraction of angles, this ought to be at least fairly easy, right? This is going to be sine is going to get us sine 180 cosine gamma minus cosine 180 sine gamma. All right, so this is AC times sine of 180 is 0. Cosine of 180 is -1. So here we get a 0 plus sine of gamma. Well, there you go. So now we have at least proven that it doesn't matter what the angle is between our two vectors. It's always going to end up being AC times the sine of gamma, which is just that angle between them. Even if that angle is bigger than 90 degrees, none of it matters. It's all good. It's just that sine of gamma that we're going to get. So, right, cool. That is the altitude we get. That then with that, we want the two areas of these two parallelograms. We already know that's going to get us that stuff over there. That's the problem, right? We know those don't necessarily mean, it doesn't necessarily mean that they're equal to each other. Because the magnitude of B and the magnitude of C might end up being, well, if they're both non-zero, then we're going to get a and if the angle between B and C is not 0 itself, right, then we're going to end up with the triangle inequality that B plus C is going to be the direct root, whereas the magnitude of B plus the magnitude of C will be some other root that is not straight. So it will be longer. All right. Right. Hey, Famish. How's it going? So if we have A cross B and we do this algebraically, right, we're going to get A1I plus A2J plus A3K hat crossed with B1I plus B2J hat plus B3K hat. We're doing all right. I'm gonna get through dot and cross products. I have one last thing to do here. No, this is going to be it. So, we're doing the cross product stuff with. Hey, Zach, how's it going? All right, A2B3 minus A3B2. Now, here's the thing. This is going to be the cross product of A2 and B3, which are J cross K, as well as A3 and B2, which is K cross J. So here's the thing, right? We did J cross K. We also did K cross J. So with this, if you remember, J cross K gets us I hat. And K plus J gets us negative I hat. So we have our negative out front here, and then we have our I hat outside. Plus, right? Do the same thing. What's going to get us J? Well, that's going to be K times, or K cross I, and that's also going to be I cross K. Again, K cross I, and then I cross K is going to be negative. What do we do to get that? Well, that's going to be k is a3 and I is b1. a3 b1 minus I, which is going to be a1 cross k b3. Okay, and then again, we need k. You're taking a break? I can't blame you. In order to get k, we're going to do I cross j, or j cross I will get us the negative version of that. So I cross j, a1, b2. This is also the only combinations that are missing, so makes it easy. And a2 cross b1. And then we look at this and we say, hey, these look suspiciously familiar. Where have we ever seen stuff like this before? And of course, it is the determinant of a 2x2 matrix. What matrix is going to get us a2 times b3 minus a3 times b2 looks like it for me. Okay, what about j? We're going to have a3 b1 minus a, what, oh, geez. a3 b1, and then we're going to have a1 b3. And then we're going to have a1 b2 crossed with a2 b1. And we've done this before, but it's been a long time. If you look at doing a 3x3 matrix, oftentimes what we do is we select a row and we say, okay, what we're going to do is in the first column, we choose C1 as our we choose C1 as sort of the pivot point, and that's going to come out front, and then we multiply by the determinant of whatever is left. This is A2, A3, B2, B3, right, plus C2. So now we go over to C2, we look at, whoops. We look at C2 and we say from here, what do we see? Well, the way that I do this, I wrap it as a torus, and I say the first term that we want to look at is down and right from whatever our pivot number was. So from C2, go down and right. Well, we can't go down because we're already in the bottom row. So wrap up to the top and then go right. Right, so that's actually going to get us A3 in the top left corner. Underneath it is B3. and then to the right again, it wraps around the other direction. So now we get A1, B1. If you want to do it some other way, you can do it some other way, but you do have to be careful. So, if we choose C3, get rid of this. C3 times the determinant, there we go. And again, go down and right. Well, we don't have anything down or right, so it's going to wrap right all the way to the left side and then wrap down all the way to the top side again. So now A1 is going to be our top left corner. And then it's A1, A2, B1, B2. So here you should notice that we have the identical, exact same stuff here. It's just that we have I hat, J hat, and K hat instead of C1, C2, C3. So that means that all of this stuff is equal to a matrix of A1, A2, A3, B1, B2, B3, I hat, J hat, K hat. To those of you who have already taken differential equations, what is that? You know what that is. Also, if you're interested in the linear algebra, you could say, oh, this is I hat, J hat, K hat up top, and then A1, A2, A3, and then B1, B2, B3, because row operations have those rules. You're allowed to trade rows at will. You can do it any way that you want. But that right there, that is the Jacobian. That is the Jacobian for vectors A and B in R3. So standard 3 space. You have I hat, J hat, K hat, and then you list the vectors underneath. And again, you're taking the determinant of it. This is the Jacobian. So if you've ever seen Jacobian, now you know what it's for. Or at least one of its many applications. There's no index in here. It's great. Goes straight to answers. It doesn't list the Jacobian anywhere in here. Oh well. You can do what you can. Okay. Time is now 1 o'clock, so we're going to head out and go see one of our other friends who are currently working on, well, we got a few. So we're going to go with learning stuff time. So if anybody is doing learning stuff, we're going to prioritize there first. Unboxing of Switch 2. Jesus. Casticlism is doing her first playthrough of Elder Scrolls V Skyrim. Rakodaclys is currently working on 6 hours of streaming, talking about pseudoscience for men. Rakodaclys is a somebody who majored in, I believe, the psychology of conspiracy theories. So I think we should probably go back over there and see Rakodaclys. So yeah, let's go over and check out his stuff. I should be back tomorrow. Tomorrow's Thursday, so we're going to be working on TTRPG prep for Titan's Grave, The Ashes of Valkana, which is a fantasy age techno-fantasy setting. And at some point soon, we're going to get a mount for this microphone, and it's going to make everything a lot easier instead of just leaving it on the desk. Okay, so yeah, that's tomorrow. Friday, we'll be doing some gamey type stuff, probably either Elite Dangerous or Baldur's Gate, depends on what kind of work we got. I do have a few, multiple, quizits, colonies that are like this close to being finished, so we might just jump through and like send multiple of them at the exact same time, or within a jump of each other, and see how that goes. So might work. Apart from that, we'll be back again on Monday for more Math Communication Monday. Hopefully we'll be back for blueprints next Tuesday, next Wednesday for math calculation again. Hope to see you all again soon. My name's Obi-Wan Pez. This is N Simplex Pachenko. Catch you next time.